Welcome to week 9 of the NPTEL course. Today we will be discussing about some more concepts on DC machines. For the last couple of weeks, we were discussing about DC machine winding, armature winding, and how it is being wound. And last week we discussed about the force, torque, and voltage, and some more governing equations in a DC motor. And today we will be discussing a couple more concepts. First, we will be looking at the power flow diagram in a DC motor. Like whenever you give a supply to a DC motor from a traditional AC supply from our homes till the motor rotates at the shaft end. So in between these two entities, what are all the losses a DC machine would face? What losses will it comprise, and what are the kinds of power loss we come across in a DC motor operation? We will see, and later we will also discuss basics on DC shunt motor, and subsequently we will be solving a couple of problems on the discussed concepts. So with that, let's start discussing about the power flow diagram of a DC motor. So let's say we have a DC motor with a known specifications, and we have given a AC supply to it. Let's draw how a typical equivalent circuit of a DC motor look like the same circuit diagram we were considering since the last couple of weeks discussion. So I'm drawing the armature. So these are the brushes, armature, like output armature terminals, and yeah, and again separately excited. So field winding would be separate, and we know inside it we will have the armature resistance, and there will be back EMF EB. It's the back EMF, and this is where we are giving the supply to the armature, and here there will be our field winding. Let's say this is the supply we are giving, DC supply to the field winding, and then current will flow, that is IF, and whatever current it draws from the supply will be IA, because it's only armature circuit. This will be armature. So yeah, now what is the input power we are giving? Total input power. If you see from the armature, and it's VA multiplied by IA, and it from the field, and we are having VF into IF. So that's the total input power whatever we are supplying to our DC motor. Now, so now I'm denoting it by P input, that is equals to total VF into IF. This is a field circuit supply, and VA into IA. Now this is the total input supply. Okay, now from this, let's say this is the total electrical input supply we are giving to the system from the system. So from this, a portion of a power will be lost first in the field circuit. So we have a field circuit, that is a coil which is having a supply of VF, and also the current IF is flowing through, and in that a couple of a portion of power will be lost, because it's having its own resistance. So I square R losses, that is the power loss. So dissipated will be some power will be dissipated across this field winding. That is, the current flowing through the field winding is IF. Let's say if the resistance of the field is RF, so IF square into RF will be the power loss. That is first power loss we will come across in the field winding. So yeah. From this, portion of power will be lost in field winding, in field circuit. Now, let's say I will denote it with a power copper losses in field. So, copper losses in field winding. So that will be I square R, right? I square is the current flowing through the field circuit. R will be the resistance of the field winding. So you can also represent this IF square into RF as a voltage and current also. If you see IF into RF is nothing but VF. That is a supply DC supply we are giving to the field winding. Now I can also represent it as VF into IF. Okay. Now, so this is the power available after the power has been lost in the field circuit. Now, the remaining power, what we call as a, now see, this is the total power. Now, VFIF and VAIA. From this, VFIF is lost in the field winding. So, what is the remaining power that is left is VA into IA. So, that is the power we call it as an input part to the armature circuit, right? So, let's say we have VI as input part to our armature. Now here a portion of power will be further lost in the armature winding. Now if you see from the figure, there is a resistance in this armature, that is RA. So obviously there will be I square R losses in the armature itself. So current flowing through the armature winding is IA squared RA, that will be the armature copper loss. So that power will be lost from whatever power is left. So the left power is VAIA. From that, copper losses will be there in the armature. So here the portion of power will be lost in armature circuit. Now this is also copper loss only because it's I square R loss, but it's in the armature is equals to current flowing through the armature, that is IA square multiplied by armature resistance. So here I write the small RA, resistance. Okay, and we can also write it as, okay, it's not VA because we cannot write it as VA because VA is the total armature supply. Let's say we will put it as a IA square into R. Now whatever power is left, that will be the gross mechanical power. So after excluding the losses in the field winding and the armature winding, we are left with the gross mechanical power. Now another portion of power will be lost from this gross mechanical power to get us to the final shaft power, that is the net mechanical power. Gross will be another quantity, net will be another quantity. Net is something which is actually useful at the shaft end, which is responsible for the rotation of the motor. So what we have to subtract from the gross to get the net is the constant losses. The constant losses, why I told about this constant losses means there are some rotational losses that will be there in the motor which does not involve any like current flowing. The current, there no need to be some kind of current should flow in order to experience that kind of loss. So even if there is no load, you have not connected any load, so no current is flowing through the load, and still there will be that loss will be there. So that kind of losses we call it as a rotational losses. So what I'm trying to say is, whenever there is no load, your motor is rotating, and your motor just have to supply to that rotational losses. So that will be some power will be lost in field. We cannot change that. Some power will be lost in the armature, and whatever power left will be, that will be sufficient to supply this rotational losses power. So that losses will always be there, even if it's a no load. In its no load condition, only the power will be delivered to supply these no load losses, that is rotational losses. Now let's put into the equation. Okay, after armature circuit, remaining power is gross mechanical power. That is, let's say, P gross mechanical. So from which we have to subtract rotational losses. Rotational losses are subtracted. To get net mechanical power. So we will see that now. Now P gross mechanical minus P rotational losses is equals to P net mechanical. We can also call this net mechanical power as a shaft power, that is a load power. So this is the power which is actually responsible to deliver to the load. This is the actual useful power at the shaft end. Now let's talk some time about this rotational losses. So what exactly is this rotational loss? So what kind of losses will be contribute to this kind of rotational losses? That's simple. Yeah. So whenever a DC machine is rotating, there will be some kind of friction, because our DC machine will have shaft will be there. It has to rotate, so it has to overcome some friction, and also the bearings will be there. The bearings will have its own friction. So this whenever a DC machine rotates, these frictional losses will always be there. Along with this friction, other type of losses are windage losses. Windage means you are rotating your machine against the wind force. So that will provide some kind of resistance, the wind in opposite direction to the rotation of the machine. So that is a windage losses. That will also be there whether there is a load or no load. Now friction losses, windage losses, and another type of losses is that is eddy current losses. So these three losses contributes to this rotational losses. So even if there is a load or no load, this rotational losses will always be there. P rotational is equals to friction losses and windage losses. Don't confuse this windage with winding. People often confuse this with winding losses. This is not winding; it's a windage. It relates to the wind, the force provided by the wind, and due to which the power loss will be there. And eddy current loss. So this particular eddy current losses we already discussed in transformer. So that is applicable here also, because there will be core even for the DC machine. The total rotor body is made up of a iron body. So whenever you take an iron body that is under influence of a magnetic field, of course there will be a path for eddy current to flow. The same way in the transformer core, the current will flow within the core. So that is causing eddy current losses there. here also AC supply will be given to the DC machine to the supply from the AC only. So the solid body of the DC machine will, let me draw here itself so that you will get a clarity. So yeah, this is the rotational losses, friction, windage, and eddy current losses. Now see, in case of now let's take these are two poles of a DC machine. Simply, I'm just showing you how eddy current losses will be there. Now, this is a two-pole DC machine. This is the part where it rotates. Okay, and around it there will be stator. Okay, and here is the rotor, like armature. On this the other coils, etc., this will be placed. Now, so these are the poles, right? This is the north pole and south pole. The field is created, the armature is rotating. So this is the body, this is the cross sectional view, but you see this is the body of the rotor. So this entire body, let's say it is made up of a solid iron. Now whenever like, let's say the body, now here the rotor body is moving under the particular magnetic field, right? So let take any closed path of the surface of this particular rotor body, and it will see maximum flux at one instant and zero flux at one instant, because it is under the influence of the magnetic field. Whenever this body rotates, whenever the air gap is minimum, it will see maximum flux, and whenever the air gap is maximum, it will see zero flux. Now this eddy current path will flow in this particular available iron, and whenever eddy currents will flow, the rotor will, like the rotor body will get heated up. So that's what we call as a eddy current loss. Now I'll just show you. This is the rotor body now. This is, let's say this is a total solid rotor. So let's say any closed path you take, so it will be under the influence of course magnets will be there. The magnets will be like this, right? So this is that particular body. Let's say this is the small closed path we took, so that will experience a eddy current will flow inside the body. That current will cause heating, and that contributes to the eddy current. So what people will do, instead of taking this entire solid thing, they will just layers. That's what we call laminations. So let's say our rotor structure is like this. This is structure, right? Our rotor will have its slots and teeth, like this. This will be a rotor structure. So here a shaft will go. So this particular thing, they will make it as a single sheet, and the same sheet they will make it another thing, and they will place on back of this lamination. So let's assume this as a single sheet. So like this sheets, they will make number of sheets and place one behind the another, and that's how they will make the entire structure of a machine. Now, what is the use of doing like this? See, here it is, the entire thing is a solid body, but here you are forming a body with single laminations of rotor. So like the purpose of doing that is, whenever you do such kind of lamination, you are reducing the path for the eddy current to flow. So the more the path, the more current will flow, the more eddy currents will be there. So you are reducing the path for the eddy current to flow, thereby you are trying to minimize this eddy current. So that's the idea of getting these laminations for any kind of machine. Now if you see a rotor of any machines, you will see the laminations are thin laminations. They are stacked together and tightly packed, such that you will get a core. So that's the reason to laminate any core of a machine, to reduce the eddy current path for the currents to flow, so that you can minimize this eddy current losses. So yeah. Now we came to know that is a net. When we subtract this net mechanical power, is what shaft power, or we can also call load power. Now, let's say in an armature circuit, we will see the justification of these equations. We will see in an armature circuit, So basic motor equations we know, right? Last year also we discussed. So VA is equals to back EMF plus IARA. Now for the figure also you can see. So this figure you see, VA is the total supply voltage minus IARA drop will give you the back EMF. That's the standard equation for any kind of motor. So these are the governing equation of a voltage governing equation of a motor. So any kind of motor, whatever be the winding, like separately excited, shunt motor, compound motor, series motor, this particular equation should always be satisfied. Voltage is equals to EB plus IARA. Now multiply IA on both sides. VA into IA is equals to EB into IA plus IA square into RA. Now EB into IA is equals to VA IA minus, I am sending IA square RA into that side. Now have you observed anything from this kind of equation? Does this equation reminds you of something? Let's go back. Here you see IA square RA is nothing but the power loss in the armature, right? Now whenever here the left power is VAIA. Now VAIA we are subtracting IA square RA to get gross mechanical power. Now gross mechanical power from the equation what we got, from the available power of VAIA, if you subtract armature copper loss, the left power is EB into IA, which is nothing but our gross mechanical power. So that's what I want to show you here. P gross mechanical power is equals to EB into, so we indirectly saying that whenever the armature copper losses occurs in an armature winding, armature circuit, the rest, whatever the power left is nothing but our gross mechanical power. If you subtract the rotational losses from this gross mechanical power, you will be ending up with the net mechanical power developed. Now, that we already discussed. Now, what my aim is to calculate the gross torque, gross mechanical torque developed. Now we know torque is nothing but power divided by speed. The speed will be in radians per second. You have to be careful about the units, radians per second. Okay. Now I know what is gross mechanical power. Let's say I also know the speed at which my motor is being rotating. Now what is gross mechanical power? EB into IA. Omega is 2 pi n. 2 pi n is by 60 if it is ns in rpm, or 2 pi into ns. So remember this ns is in rps. Let's say let's not write ns, it's too confused. So 2 pi n, that is rps, rotations per second. Now did you remember the last week discussion? Not last week, 2 weeks before, the first session on DC machines. So in that we derived the equation for this EMF induced, torque, and also force. So if you remember that the equation of EB we derived, that is EMF induced, is PZ by A, that is number of poles multiplied by conductors divided by parallel paths, into phi into N. This is nothing but EA, and IA is already there. Now speed get cancelled out, and whatever you are left with, PZ by 2 pi A multiplied by phi multiplied by IA. This is nothing but T gross mechanical power developed in a motor. So If you remember the same kind of equation we also derived in that last week along with EB equation. We took the force experienced by a motor by each conductor. Then we calculated BIL of each conductor when we multiplied with the total conductors in that machine to get the torque developed. So again, we came to the same kind of equation here as well. So yeah, I'm just justifying this governing equations of a motor. So if you take any kind of motor, these are the some basic fundamental equations. EB voltage is equals to K phi speed, K phi omega or K phi n, and torque is equals to some constant. Here it is Pz by 2 pi a, K multiplied by phi into Ia. So these two governing equations of voltage and torque are very important when it is dealing with the DC machines. So yeah, as a summary of this power flow diagrams, I just want to give you a pictorial representation of the total power flow. I'll just whatever we discussed, I will put it in a picture. Then that will be easy for you as well to understand the losses in a motor. So if you remember what we discussed today, power flow diagram, we started with the total supply, whatever we are giving it. So let's say input power is VFIF. Whatever we discussed, I am putting it in a diagram. So VFIF and VAIA. Now what is the first loss we discussed? That is a loss in the field winding, field copper loss. Let's say this is my total input power, that is P input, and some loss I have experienced it here, that is field copper loss. That is IF into RF, which is also equals to, sorry, IF square RF, I square R, which is also equals to IF into IF into VF. That is P copper loss of field. And okay, now I will proceed. And from this power, what else I lost next? See, now I have lost IF-VF from this, sorry, IF-VF, and whatever left is VA-IA, right? That is input power. I have lost some power here. Input power to armature, that is VA into IA. Now this has been fed to the armature. Now again I have lost some power, that is armature copper loss. Now that is P copper loss of armature, which is nothing but IA square RA. So in VA, IA square RA is lost. So what is the name of that power? What we discussed now? What will be at the end? What will be the power which will be obtained after subtracting this armature copper loss? Anyone? It is nothing but gross mechanical power developed. Okay, that is what is that expression for it? EB into IA. That is the gross mechanical power. Now we have to subtract the no load losses. What we discussed, that is rotational losses. Now we subtract the rotational losses from the gross mechanical power. Now what are the rotational losses we discussed? Friction, windage, and eddy current loss. So once you subtract these rotational losses from the gross mechanical power developed, you will be ending up with P net mechanical, that is also called as shaft power. So this is typically the power flow diagram we usually come across in a DC motor. Now we are giving a supply, that is both field supply and armature supply. We are losing the power in the field winding, that is IF square RF, which is also VFIF. We are left with VAIA, that is the power input to armature. In that we are losing some power to armature copper loss, IA square RA, and whatever power left will be gross mechanical power, that is EB into IA. From that, if we subtract the rotational losses, which are constant losses, friction, windage, and eddy current losses, we will be ending up with the shaft power. So this is very important power flow diagram when it comes to DC motor. So many numericals are there in order to solve the losses in a DC machine. So if you remember this diagram perfectly, it will be very easy for you to do solve such numericals, because you know what all the losses will be there, and you will be clear about the concept of losses and where it will occur, and what current causes which losses, and what are the constant losses, what are no load losses, and yeah, so every problem related to losses will be very simple if you just remember this diagram. With that, let's move to another small discussion, that is DC shunt motor discussion. One second. Okay. Yeah. Okay. Let's see a few minutes about. Let's discuss a few minutes about this DC shunt motor, and we will proceed with the numericals on this. So yeah, it's no different than whatever we discussed. So whatever may be the winding is separately excited, series excited, shunt excited, the motor governing equations will be same wherever. But just the diagram, the connection diagram of the DC motor will just change. So see, we discussed the separately excited. So field winding will be in separate section that is separated from the DC motor. Now, if you see, let me just draw. Now, this is the armature, and this is armature resistance. This is the back EMF. Everything will be same, and these are the armature terminals, right? Now, if you see here, usually what we have, field winding will be like this, right? Now I'm just connecting this in parallel with my armature. So then it is called as shunt. This is RSH, and yeah, whatever current is flow, this is IF, right? And yeah, now this will be the supply we give. Now what you observed, see, now if this is the kind of winding, and both are field winding and armature winding are in parallel. So whatever supply you give, that is nothing but the same supply for both field and the armature. So there is no different supply like VA here, VF here. The both are same. That is V. So that's why I named it as a V. That is the common supply for both armature and field as well, because both are in parallel. Now, if you see, let's say whenever we connect it in this fashion, it draws, my motor will draw some current, and also the field winding will draw some current, right? Now let's say I call the total current that is drawn from the supply as line current. Line current I drawn from supply. Now I is nothing but summation of two currents.
field current and armature current.
Right. Just because it's in a parallel connection, current will be divided. IF plus IA. So let me also just write IA here. Since it's parallel, current will be divided. Voltage will be same across the parallel branches. Now I is nothing but IF and IA. So based on the resistance of field winding, based on the resistance of armature, the current division will take place. If it is more resistance, it will be there. Usually field will have higher resistance. Armature resistance will be very less inside the motor. So based on that, the current division will be takes place. Again, I'm saying whatever type of winding it is, my equations, my voltage equations and torque equations will be valid. So what is the motor equations we discussed? EB is nothing but V minus, yeah, Ia Ra. Now we know this is nothing but some K, K1, like let's say this is K, some kind of constant K into phi and N. That is, this is the derivations we looked at since the last 2 weeks. Today also we discussed this. So these equations will remain same, and electromagnetic torque developed will be some K. This is some K dash phi into Ia. This is something that my load torque. Now these two equations will always satisfy whatever may be the equations. So you see EB and RA, the total drop will constitute EB plus IRA drop will be the total supply. The same supply will be coming, will be seen across my field winding. So divided by resistance RSH, shunt resistance will give you the field current that is flown. So this is more or less basic about the DC shunt motor. It is pretty simple. All the equations will valid here, except that two windings are in parallel. So if you see, if you want to calculate the field current, if you know the armature current, you supply that armature current from the supply current, so that you will get the field current. If you know field current to get the armature current, you subtract that field current from the supply. So that kind of simple network analysis circuit basics will be, if you know that, you can solve problems on this DC shunt motor. So with the concepts we learned today, that is power flow diagram in a DC motor and also the basics on the DC shunt, let's solve some problems on DC shunt motor. Now please,
Sir,
yes,
DC shunt motor, also known as constant flux motor.
constant flux motor. I cannot say that. Why it should be constant flux motor? See, whether it's a constant flux or not, it depends on the field current. As far as the motor is in linear mode operating, your flux, field flux will be proportional to the IF. IF keeps on changing. Now, if the input supply voltage is fixed and the shunt resistance is fixed, my IF will always be constant. So if IF is constant and your motor is rotating in the linear region, my field flux generated will always be constant. So that's okay. Even you can also get the constant flux in separately excited motor as well, because there will be separately excited machine. You will be have to give separate DC excitation there. If you keep the DC excitation same and you are not varying this resistance, the field resistance, you will get constant flux there. Yeah, it depends. Like if you are not changing the IF here and the shunt resistance is always same, it is a constant flux machine. But that's not the case always. We cannot generalize like that. Maybe if you keep the shunt resistance same, yeah, then it could be. Now, see, okay, in the question here, we are given with a 200 volts DC shunt motor. At no load it's saying, so there is no load connected. So I'm just telling you, at no load what are the losses it has to supply. We just discussed. So what are the losses the motor has to supply no load? They are rotational losses. Okay. Okay. So a 200 volts DC machine is there. Okay. I'm just noting down the data. V is equals to 200 volts. It draws 4 amperes from the supply. Okay, let's first draw the diagram, then it will be easy. Okay, I'm drawing the field. This is the motor armature. This is the field, and this is the supply. Now, since it is a DC shunt motor, whatever supply I give is same to field and armature as well. Please keep in mind because in a shunt motor there is no separate supplies to the field and armature. This is back EMF. This is RA. RA is given. Okay, let's write that also. 0.8 armature winding, and EB is given. No, EB is not given. Let's keep it as EB. And is shunt resistance given, and the field resistance, which is nothing but shunt here, it is 200 ohms. Okay. The DC shunt motor draws 4 amps from the supply at no load. Okay. Now there is no load. To the shaft of the motor, I have not connected any load. Now at this condition, I am drawing 4 amps. Okay, good. Now the motor is drawing 41 amps while loaded. Okay, that is next condition. Let's see the condition for now. Let's say there is a shaft connected here, and I have not connected any load. So when there is no load, 4 amps is being drawn, and this is IF, and this is IA. Okay, we don't know what is IA and we don't know what is IF, and let's see what was the question asked. Okay, so we were asked to estimate the speed under this load. Okay, and okay, in the equation it also given as it's 1100 rpm, that is no load speed. Okay, and no load is equals to 1100 rpm. I used capital N because it's in rpm. I should have used N small n if it is in rps. Okay, and just it's a convention, you also keep in mind so that you won't make mistakes while solving. Okay, yeah, I have noted all the data. I have made the diagram for my DC shunt motor and represented all the values given and also the no load speed. Now what was asked to me? We are asked to estimate the speed under loaded condition. Now in order to calculate the speed, I need to first calculate what are the back EMFs at each case. At no load, what my back EMF is, and at full load, what is my back EMF. Once I get back EMF, and we know that our back EMF is proportional to K phi speed. In that phi is nothing but proportional to my field current, which I can always calculate. Can anyone tell me how can you calculate IF? Very simple. Even by seeing figure, you can say how much is IF.
Supply voltage by field resistance.
Yeah, correct. You see, supply voltage is 200 and field resistance is 200. So IF is nothing but 1 amp. So that is always very easy to calculate field current from the diagram. You're correct, Saurabh. So you divide 200 by 200, you will get the field current. Now you calculate back EMF for the both cases, no load case and full load case, and then you can easily get the speed for the loaded condition. Now let's proceed with the calculation. So first thing I will do is calculating the field current. Okay, I will just do it. No load condition and loaded condition, because there are two conditions, 4 amps in no load, 41 amps in loaded. So I just don't want you to confuse for that, so I made two different sections. And in no load, let's say field current 1 is equals to V V divided by RF, that is RSH, because even one notation I am using it for no load and 2 I will use for loaded. If there is no notation, it means that both are same in both cases. Why I am saying it? Because even if it is loaded or no load condition, My supply is same V. That's why I'm not giving V1 or V2 for supply. And this RF, even my RF is not changing in both conditions. So 200 divided by 200 is equals to 1 amp. Let me calculate IF2, that is second field current in loaded condition. Loaded condition voltage is same, RF is same. So I'll be ending up with same 200 by 200 is equals to 1 amp. So my IF1 and IF2 in both cases are same. Now let me find armature current. So yeah, can someone tell me what is my armature current in no load condition?
Minus field current.
What minus field current?
Supply current minus field current.
Correct. So since it's a parallel connection, you have to supply line current minus IF1. So in no load condition, my no load current supply is drawing 4 amps minus 1 is the field current. So 3 amps is my armature. Now in the loaded condition, it was given in the problem that my supply is drawing 41 amps. Field current is again same. So now I got IA1 and IA2. One second, just yeah. Okay, yeah. So we have got the both armature currents in both cases, loaded and no load. Now I will proceed with the calculation of EB1 and EB2. EB1 is nothing but V minus IA1 and RA. My armature resistance won't change. It is also constant. EB2 is equals to V minus IA2 RA. So please calculate along with me and tell me what is the value of EB1 and EB2. IA1 is 3 into zero point 0.8 and here it is 200 minus 40 into zero point 0.8. I will also calculate, please calculate with me.
Equal to 197.6.
197.6 EB1.
Yeah,
Okay. Let me also tally the answer with you. Yeah. 197.6 is EB.
and EB2 equal to 168.
Okay. How much is EB2?
168. 168.
Okay. 196.8. Right. Okay, always mention the units. So yeah, so we got EB1 and EB2, but if you see, I will just go back. See here the relation EB is equals to K phi IN. K is always constant. Whatever may be loaded condition, no load condition, once you decide the machine, the poles will be fixed, conductors will be fixed, parallel paths will be fixed. So K is always constant, and this flux is always dependent on field current. Whenever the motor is operating in linear, the flux developed will be proportional to my field current, and this is the speed. So with that relation, let me take the ratio
Sir,
EB1. Yes.
EB2, that value 168.
Okay. Okay. Sorry. I'm sorry. It's 168. Thank you, sir, for pointing it out. 168. Yeah. Thank you. So yeah. Proceeding with this, EB1 by EB2 is nothing but K phi 1 N1, K phi 2 N2. So N1 is no load, 1 is no load and 2 is no load, full load, loaded condition. Now I phi 1 and phi 2 are proportional to my field current, right? Mm, okay. K is always constant, so that will be okay. And phi 1 is IF1 and N1 and IF2 N2. But one more thing you have to make sure here is my field current is also same. IF1 is 1 amp and IF2 is also 1 amp. So even these two get cancelled. Now whatever is left is N1 by N2, and what is the question asked in the problem, that is N2, that is speed at loaded condition. Now N2 is nothing but EB2 divided by EB1 multiplied by N1. N1 is nothing but 1100 RPM, right? We'll just, I will write it here. Now my N2 is equals to, EB2 is 168 divided by 197.6 multiplied by 1100. Can someone tell me?
Nine three five point two.
Okay, 935.2. It's 1100. One. Let me also confirm with you. 1 second. 168 by 197.6 into 1100. Yeah, 935.22. You are right. Please, other students also please tally with the answer told by her.
Sir, right.
Okay, thank you.
935.2.
Great. So yeah, that's how you calculate any kind of loaded condition for any kind of operating conditions. Now it's no load versus loaded, and next time they can also ask two different loaded conditions. Let's say at one loaded condition it is drawing 40 amps, another loaded condition it is drawing 50 amps, and what will be the new speed? What will be the new voltage? So any kind of such problems, you start with the basics. What is the field current? How will calculate? What is armature current? And what is the voltage back EMF developed. So then you know the relations. E is equals to K phi omega, torque is equals to K phi into current. With that equations and these basics, any problem with the DC motors or DC machines will be very easy. Now, if you have understood that, the second sub part of the equation is we have to estimate the load torque or shaft torque. We already discussed the shaft power and load power. So if you divide that shaft power or load power with the speed of the machine, you will get the shaft torque or load torque. That's not a problem. Now, this particular torque and power calculations will involve our losses discussion. So that's the reason we have discussed thoroughly what are all the losses present in a DC motor. Now let's proceed step by step to achieve the torque point. That is a shaft point, right? That is the end of the point. So let's go step by step, and it will be very easy to calculate the shaft torque. Now I'm just writing it here. Finally, I need shaft torque. Shaft torque is nothing but shaft power divided by the speed of the machine. So this will be in the radians per second. Right. Now I know the speed of the machine. Just now I calculated 935.2. That is the speed of the condition in loaded condition. Now, do I know the shaft power? No, we don't know the shaft power. So how can I get the shaft power? So let's go back to our power flow. Whenever you are stuck, just go back to basic, and you see what I have to calculate. What is the data I am having? Now I need what I need. Shaft power is what needed. Now to get shaft power, I need to calculate VAIA. Like let's say this is shunt motor, right? So the total input to the armature, that is VAIA. I need to subtract IA square RA, and I need to subtract gross mechanical power, gross mechanical power will be there, and I need to subtract rotational losses. So from the input power to armature, I will subtract armature losses and I will subtract rotational losses to get the shaft power. Now I will write it again here. In order to, I will just make it a line here, and I will write what all we needed, and I will calculate that here. So now see, this is my ultimate goal. I need to achieve at the shaft torque. So for that I need shaft power. Do I know shaft power? I don't know. Now P shaft is equals to VA IA minus armature copper losses, IA square RA minus rotational losses. That is nothing but sorry. Okay. So rotational losses are nothing but no load losses. That also we don't know. So in this, what all we know? VA we know, that is nothing but supply. Do we know armature current? Yeah, we know armature current in both loaded condition and no load condition as well. So since it is a loaded condition, yeah, we know how much is IA, that is 40 amps we got, and RA we know, IA we know, RA we know, and we don't know this rotational losses. Now, how to calculate rotational losses? So rotational losses are nothing but we know that is a no load losses, right? P rotational losses, how to calculate. Now let's go back again to our power flow diagram. Again, whenever you don't know, just go to the basic. You don't actually solve for the question. You go from the basic. So I need to calculate rotational losses. Rotational losses are nothing but there is no shaft power, because in order to get rotational losses, that is nothing but the no load power, right? Whatever losses I'm experiencing in the circuit, let's say I know the input power to the armature. So already I have excluded the field losses. Now, if you just subtract this armature copper losses from your input power to the armature, whatever power left at this section, that will be your rotational losses only, because there is no shaft, there is no load connected, you don't need any power for the shaft. So whatever power left at this end, at this point, after subtracting the armature copper losses, will be rotational losses. So at no load condition, you calculate input to the armature and you subtract armature copper losses, then you will get the rotational losses. P rotational is equals to VA IA. And the most important thing you have to keep in mind, it is at no load condition, because the supply, the losses supplied at the no load only rotational losses, because I have not connected any load to the shaft. So I have to specify here the armature current at this condition is no load current. Now you subtract IA square RA at no load to get the rotational losses. Now tell me what is the voltage supply. Now it's just substitution now. 200 multiplied by what is the no load current. The no load current is 4 minus 1, we got 3 amps, minus 3 square multiplied by 0 0.8, 0.8 or 81, 0.8. Okay. Now please tell me the rotational losses.
592.8.
Okay, good. I will also check that. Okay, that's correct, Shubham. 592.8 watts. These are my rotational losses at no load conditions. So at no load condition, my motor will rotate just to deliver this rotation losses. Now go back to our required equation. Now I know this rotation losses. I know Ia square. I know Ra. I just have to get the shaft power. Once I get shaft power, I will substitute here to get the shaft torque. Now please calculate shaft power along with me. Same equation. VA Ia 200 multiplied by what is IA here? Armature current in loaded condition 40. Please don't make mistakes like here at no load condition, no load condition. You have to make sure what currents you are using. IA square into RA minus rotational, that is 592.8. Please tell me the answer. Forty square into 0.8 minus 592.8. Anyone?
6127.2.
That's exactly correct.
6227.
Okay, so Vidya also seems to got the same answer. Even I got same answer, 6127.2 watts. Correct, Shubham. Correct, Saurabh and Vidya. So yeah. Now, since we got the shaft power, now what is the question asked? We just have to calculate the load torque or shaft torque. Now it's simple. What will be my shaft torque? Will be P shaft divided by omega. Now omega is in radians per second, right? It is 6127.2 divided by omega is nothing but 2 pi ns by 60, 2 pi n by 60. If the n is in RPM. What is the full load speed? Load speed we have calculated in the first problem. 935.22 RPM divided by 60. Please calculate this and let me know the final answer for the shaft torque.
Two point 5633.
Sorry, come again.
62.5633.
Yeah. So Vidya, you also got the same answer.
Yes, sir.
Okay, great. Even I got 62.563 Newton meter, and this is our shaft torque or load torque. Simple. So yeah, how we achieved at this, how we arrived at the shaft torque. Again, just giving a recap of this problem. We know our shaft torque is nothing but our power divided by the speed of the machine. But in order to calculate our output power, that is net mechanical shaft power, we need to start from the first basic. We have the input. I will have some field losses, and then I arrive at armature input. I again subtract my armature copper losses. Then I arrive at the gross power. I will subtract my rotational losses, and I arrive at the shaft power. But what I don't know here is my rotational no load losses. But to calculate, in order to calculate my no load losses, my data was given to me. What is a no load power, no load current, what is a no load voltage, what is no load, all other parameters were given. I just have to calculate no load losses and substitute that to get the shaft part. And the previous problem is the first subsection of the part is where we have to calculate the speed of the machine at a given load. At the given load means we already given that the motor is drawing 40 amps 40 amps into its armature while loaded. So with that information, we calculated the speed at that condition. So yeah. So to recap the concepts we have discussed today, I will just quickly tell you what all concepts we have discussed. Um, 1 second. Yeah, we started with the power flow diagram of a DC motor. We saw for a separately excited motor or a stud motor, it's applicable for any motor. So we started with what is the power input and what is the copper losses in the field. What are the types of losses we experience in armature, and how we arrive at a gross mechanical power, how we arrive at a shaft power, and also we talked about the rotational losses of a motor and how laminations of a motor are done so that we can reduce the eddy current losses. We will minimize the path for the eddy current to flow so that we will achieve better efficiency. So yeah, if you see here, we know that P net mechanical is the final power, right? So the efficiency of a machine is nothing but P net mechanical divided by P input. This is another important relation. So efficiency is nothing but output power by input power. Here my output power is net mechanical power. Input power is again VA IA plus VF IF. So yeah, we discussed that as well, and then we discussed how torque and power can be calculated from that relations, and we justified with the basic derivation we did 2 weeks before with the force equations and conductor. We took the individual conductor force and arrived at the torque. So we again arrived at the same equations from this kind of analysis as well. So, and then we saw the comprehensive power flow diagram in a DC motor and how the losses will be picturized in a pictorial representation. So, we will arrive at the shaft power at the end. And then we saw a basic construction of a like basic equivalent circuit of a DC shunt motor where our field winding and armature winding will be parallel to each other having a single supply. And then we saw the two governing equations of voltage and torque developed in a motor, and those two will be same for any kind of winding, whether it's shunt or series. Now, based on the concepts, we solved two different questions, and I'm not going to repeat what we did in these two questions. So, yeah, with that, I end today's session. And if you have any doubt in today's discussion, please do ask me, and we will just discuss that here. And if there are no more doubts, uh, it's okay. I hope you have understood. And please, if you have any doubts regarding other concepts as well, you just raise those questions in the discussion forum. We will definitely get back to you with the solutions on that. And with these concepts, I hope you can now able to solve the assignments more easily. That will be provided to you weekly assignments. And please don't forget to attend the session on 7 p.m. because there you will be discussing other concepts of our DC machines. There will be the D axis, Q axis, and some more concepts of DC machines. Please don't miss the session which is scheduled at 7 p.m. And with that, if you don't have any doubts, I thank you for patiently attending the session and listening to me, and also giving answers to me while we solving together. So in that way, the session would be really interactive, and it will be very supportive to each other to conduct sessions. So thank you again for being patient and coming to session and giving your time here. Thank you. We will meet next week same time, 4 p.m.
Thank you, sir.
Thank you, Vidya.
Thank you, sir.
Thank you, sir.